Hello and welcome to a new video and start of a new journey in our continued quest of trying to master geometry. And our today's agenda for the next few sessions is going to be similarities. So hopefully by now we have already mastered congruence and we not only understand the rules of congruence, we have also seen that it works like a tool for us in deriving so many other theorems, from triangles up to circles, properties of chords. All of these we derived using the idea of congruence. So it is a very important tool for us. Similarly, another very important tool for us is going to be the idea of similarity. What are the properties of similar triangles and what is the criteria for two triangles being similar? Because once again, if I can conclude that two triangles are similar to each other, a lot of other information opens up for me and I can use those results to solve problems or derive even more theorems. So that is going to be our agenda to master similarities. But before we begin with similarities, we will start with an even simpler idea known as the basic proportionality theorem. So let's get started with that first. So what is the basic proportionality theorem? That if there is a triangle ABC and I draw a line DE parallel to one of the sides BC. So the information given to me is that DE is parallel to BC. This line will divide the sides AB and AC, the other two sides, in the same ratio. That means the ratio of AD is to DB is going to be the same as the ratio of AE to EC. That means, say for example, and this is just to get familiar with the idea, if this is 1 units and this is 3 units, the ratio is 1:3. The ratio of AE and EC is also going to be 1:3. And remember, I am not saying that if this is 1 units, this is going to be 1 units. I am saying if this ratio is 1:3, this ratio is also going to be 1:3. To be even more clear, right, this is 1x, 3x and this would be 1y and 3y. Because in this case, it might look like these two parts are equal. So let me draw another triangle where the third side is very, very long, so that I can see the idea in action. And I draw a line parallel. And let's say the ratio of these two parts is 1:4. The ratio of these two parts is also going to be 1:4. So in this case, there might be a chance of confusion, but in this case, I can see this side is obviously way bigger than this side, right? That means if there is a line parallel to one side, it will divide the other two sides in the same ratio. To be even more specific, AD upon DB is going to be equal to AE upon EC. I can very quickly give you a problem also. I tell you this is 1.5 centimeters, this is 3 centimeters. You know this is 2 centimeters. How much is this going to be? So you can see here the ratio that the line DE divides the side AB in is 1.5:3 or 1:2. Same ratio is going to work here, 1:2. This is already 2, that means this was going to be 1 centimeter. So this was obviously a very simple application, but before we get into the details and start using it to solve problems, and remember in geometry, if you know the idea, the problem solving is going to be very, very easy if you are familiar with the idea. Otherwise it might be next to impossible because you might not be able to think at all what tools to use, right? So we got the result, but first of all, before mastering the application, we want to question this result itself and prove where did this come from. Because that process of proving itself is going to do wonders for you. It will improve your comprehension of these basic similarities, connection between figures. It will improve your problem solving skills, and most importantly, it will improve your why asking, and which is the fundamentals of problem solving. You ask a why and the problem solving becomes easier for you, right? Because essentially a why is asking the logic. So you're constantly working with logic. So let's figure out why this result is working for us. So first let me make the triangle a little bigger so that it's easier to study. A, B, C and a line drawn parallel D, E. So given information, DE is parallel to BC and I wanted to prove that AD upon DB is equal to AE upon EC. So this will take a few steps, but the first time it might look very unfamiliar, but do it a couple of times and the idea would be visible to you very, very clearly. So I want to reach here and this is the information given to me, plus I have all the tools, whatever tools I have picked up earlier, right? So let me start working on this. The first thing that I'll do is I'll draw a perpendicular from E on AD, and let's say call it N. Perpendicular means this is going to be 90 degrees. And also if I think of triangle ADE, EN is going to be the height for it, right? This is the base and this is the height. If you want to draw it again, especially for beginners, this is the base, AD is the base, and this E was the vertex here, and you're drawing a perpendicular, so this is the height of the triangle. So if I think of triangle ADE, there will be more figures, but I'm going step by step, so the process is very clear to us. If I think of triangle ADE, area of triangle ADE, what is the area of a triangle? Area of a triangle is half into base into height. This idea again we have worked out, derived, proved, so we know the area of a triangle is going to be half base into height. So just a couple of pointers. So you can obviously have this as the base and this as the height, but sometimes the altitude might lie outside of the triangle. There should not be a problem at all. So this would be the base and this would be the height that you would consider. So just a couple of ideas to get started with before we start working on this. So the area of triangle ADB is going to be base, AD is the base, and EN is the height. Is going to be half, AD is the base, AD into EN. So before we go any further, write this result down for yourself because you'll be using it later. Let me create another story. Let me connect B and E. And now I'm thinking of triangle BDE. Triangle BDE. If you think of triangle BDE and if you rotate your point of view and consider BD as the base, once again EN is the height of the triangle BDE. How? If you want to draw this again for yourself, put B here, D here, and something like this. This E is here, and you can see that EN, the perpendicular, is the height of this triangle. So EN is the height of the triangle BDE, because remember the height can fall outside the triangle also. That should not be too much of a problem. And in case you're not familiar with the idea, now you're learning. This is the base and this is the height. The first time that you look at it, it might be very, very difficult, but repeat the process a couple of times and hopefully with time the process will get better and better. So triangle ADE, the base was AD and the height was EN. For triangle BDE, the base is BD and the height is EN. So let me write down triangle BDE is equal to half DB into EN. And for now, let me think of the ratio of the areas of the triangle ADE and the triangle BDE. And if I want to create a ratio numerator by denominator, this half gets cancelled. This EN is also getting cancelled. So I'm left with AD upon DB. So once again, let me just stay with the final result and you can write it down for yourself somewhere. AD upon DB. So AD upon DB. So I'm heading somewhere here. I have maybe halfway through. Now, maybe forget this line altogether and draw another perpendicular from D to the side AE and call it M. So now this is the perpendicular. Now think of the same triangle ADE. AE is the base and DM is the height. AE is the base. I'll not draw this again. Tilt your head and watch it like that. AE is the base and DM is the height. So once again, if I look at area of triangle ADE, is going to be half AE as the base and DM as the height. So another result for you. Now I will join D to C, and now I look at triangle DEC and think of EC as the base. If I think of this triangle, isn't this the height for triangle DEC? Stop, hit pause, maybe draw it out for yourself in the orientation that you're comfortable with. I'm saying this is the base and this is the height for the triangle DEC. Same idea as earlier. So once I get that, I have area of triangle DEC is equal to half of, I have EC as the base and once again DM as the height. So actually the same idea that you worked out earlier, repeating once again. So going from here to here also, your speed should pick up, and your visualization should improve. So this half gets cancelled again, this dm gets cancelled again. I'm left with AE upon EC. I'm left with AE upon EC. So I've got the two paths. How do I connect them together now? To do that, we will use another idea that we picked up in our journey, and the idea was that if I have two parallel lines and there are triangles between these two parallel lines with the same base, the area of these two triangles are going to be equal. Area of triangles between the same parallel lines having the same base is equal. Another idea that we have worked out in quite a lot of detail. So I should already be familiar with this idea and being applied here, so it's getting revised also. DEC and triangle BED, both of them are between the lines DE and BC. That means they are between the same parallel lines. And if you think about it, for both of them, this DE is the base or the common base. Just change your orientation again. Think of this as the base. DEC is one triangle, and think of this as the base. DEB is another triangle. So this is the common base. These two triangles are between two parallel lines, the same parallel lines, and have a common base. That means their area is going to be equal. That means area of triangle BDE is equal to area of triangle DEC. And what is the theorem behind it? Triangles between the same parallels having the same base have equal area. So I know these two triangles are equal to each other. Now notice this result. This was triangle ADE upon triangle BDE. This one was area of triangle ADE upon area of triangle DEC. We have already worked out the values, but instead of DEC, area of triangle DEC, can I not write area of triangle BDE? So I can write area of triangle BDE. So this is area of triangle ADE upon area of triangle BD. This is also area of triangle ADE upon triangle of BD. That means these two are going to be equal to each other, and I finally reached the last step. AD upon DB is equal to AE upon EC. So now you can surely say, when you draw a line parallel to one side, it will divide the other two sides in the same ratio, because the ratio of AD upon DB is going to be the same as AE upon EC. Why? You have just proved why. So let us now apply the idea in an actual problem. This is the figure given to us, and I know that LM is parallel to BC. That means this line is parallel to this line, and also that LN is parallel to DC. So LN is parallel to DC. And it is given to me that AM is to MB is 1:3, and the question is, what is AN is to ND? So this figure, these two lines are parallel and these two lines are parallel, and I have some information about this side. So how will I go about doing that? And the beginning point should have been obvious to me. These two lines are parallel. That means I'm thinking of triangle ACB. This is a parallel line to this side. That means this line will divide the side AC and AB in the same ratio. That means if the ratio of AM is to MB is 1:3, the ratio of AL is to LC is also going to be 1:3. And again, we're talking about ratios, not actual values. So this is part of the story that I've got, and now it should be very, very clear. This line is parallel to this line. That means now if I think of the triangle ACD, this line is parallel to one side. That means it will divide the two other sides in the same ratio. And I know AL is to LC is 1:3. That means this is also going to be 1:3. So my question was, if this information is given to me, what is the ratio of AN is to, ND? Your answer would be 1:3. And even if the question was AN is to AD, it should not be too much of a problem, because I have worked this out. Let me say this is 1x, this is 3x. My question is, what is the ratio of AN is to the whole thing? That means 1x plus 3x, 4x. That means AN is 1x for me and the total is 4x for me. So xx will get cancelled and I will get 1/4. So once I have the ratio of the paths, the ratio of a part to the whole, finding that out should not be too much of a problem for us anyway, especially if we have already mastered ratios. Even if not, it's a very simple idea. Just work it out for yourself and you will see. Though, once again, I can create a theorem around it. I can say, if there is a triangle and I draw a line parallel to one side, it will divide the lines in such a way that the ratio of A is to C, C being the whole thing, will be the same as the other side, A is to C. But this idea can be derived very quickly, because if you have the paths, if this is B, that means this will also be, if this is B, this is A is to B, this is also A is to B. And if C is the total, the ratio is going to be A upon A plus B. The ratio for this is going to be A upon A plus B. I'm assuming that C is equal to A plus B, so the whole thing. Don't get confused in the names might get confusing. Consider the idea. If this is 1 unit, this is 3 units. I know the ratio is 1:3. I know the total is 4. So the ratio of the part to the whole is going to be 1/4. The ratio of this part to the whole is going to be 3/4. So jumping from this idea to this idea should not be too much of a problem. An almost immediate application can be a trapezium. So a trapezium is where one of the sides, one of the opposite pairs of sides is parallel to each other. So if I call this A, B, C and D, I know in this case AB is parallel to CD. AB is parallel to CD. So this is the starting point of the trapezium, that a trapezium, a pair of opposite sides is parallel to each other. If both the pairs were parallel to each other, you would go into the theory of parallelogram. But as of now, staying with the trapezium. And now I draw a parallel line, say E and F to DC, and because it is parallel to DC, it will also be parallel to AB. So I draw a line parallel to any of the sides. And once again, I will notice very similar results to what I have just worked out, that this line EF will divide the sides in the same ratio. That means AE upon ED, AE upon ED is going to be equal to BF upon FC, is equal to BF upon FC. So once again, somebody can share this as a result, but my question again would be, how do I prove this? Because proving this itself is a challenge or a problem for us, right? So let's get started. What I will do is, I'll connect A with C so that I can get triangles into play. Now I can see very quickly AE upon ED, let me call this point G. AE upon ED is going to be equal to AG upon GC. Why? I'm thinking of triangle ADC, this triangle only, forget the rest of the story. EG is a line parallel to one of the sides, that means it will divide the other sides in the same ratio. So whatever is the ratio of AE upon ED is going to be the ratio of AG upon GC. AG upon GC. And now take the same step forward and think of triangle ABC. Triangle ABC is going to be like this. And once again, GF is a line parallel to one side of the triangle. Only your orientation has changed. The idea is still going to be the same. The ratio of AG is to GC is going to be the same as the ratio of BF is to FC. That means because of this triangle ABC and this being a line parallel to AB, I can say AG upon GC is the same as BF upon FC. So AG upon GC is equal to BF upon FC. And therefore proved, because you said AE upon ED is equal to AG upon GC and AG upon GC is equal to BF upon FC. That means this is equal to BF upon FC, and you can directly jump here. So even when you see a trapezium and you see a line drawn parallel to one of the sides, you know that line is going to divide the other two sides, the non-parallel sides, in the same ratio. So let's try one more problem and try and apply the theory that we have learned. This is the information given to me, that PQR is a triangle. PS upon SQ is equal to PT upon TR. This is one part of the information. And the other is angle PST is equal to angle PRQ. This is the other piece of information given to me. And one more piece of data is that PQ is equal to 6. So PQ is equal to 6 units. And your question is, what is the value of PR? So let's get started. It was not given to me that ST is parallel to QR, but the moment I look at this piece of information, that the ratio of these two paths is the same as ratio of these two paths, I know ST is going to be parallel to QR. So ST parallel to QR is also something I know. The moment I have this, I notice ST and QR are parallel lines and PQ is a transversal, and this angle are corresponding to each other. That means whatever is the value of angle PST, the same value is going to apply for angle PQR. And I already know angle PST is equal to angle PRQ. This angle is equal to this angle is equal to this angle. That means these two angles are equal to each other. Now, using the theory of isosceles triangles, if two angles are equal to each other, the opposite sides are also equal to each other. Now it's done. PQ is 6 units, so PR is also going to be 6 units. A very interesting problem. This is the figure given to us, triangle ABC, and it is given to me that DE is parallel to AC. And pay attention here because there are a couple of lines involved. So DE is parallel to AC, DE is parallel to AC, but DF is parallel to AE. A was connected to this other point E, so DF is given to me parallel to AE, not AC, right? So I have this information and I want to prove BF upon FE is equal to BE upon EC. BF upon FE is equal to BE upon EC. This is what we want to work out. And again, converting the proof into an actual problem is not very difficult. I put in a few values here and I ask you for the values, the same thing as proving it basically. So how would I go about doing that? Let me look at what I have for obvious. I know that DE is parallel to AC, right? Let me put a little P here to mark them as parallel. So DE is parallel to AC. That means DE is parallel to one side of the triangle. That means it is going to divide the other sides in the same ratio. That means BE, because DE is breaking this BC into BE and EC. That means BE upon EC is going to be equal to BD upon DA, is equal to BD upon DA. This is from this big triangle ABC and DE being parallel to AC. So this is one part of the story, and I probably reach midway because now I'll change my point of view and think of triangle AEB. And now I'm thinking of this particular triangle, and DF is parallel to AE. DF is parallel to one side of the triangle. That means it will divide the other two sides in the same ratio. That means BF upon FE is equal to BD upon DA, is equal to BD upon DA. And you already saw BD upon DA somewhere. So BF upon FE is equal to BD upon DA, but BD upon DA is also equal to BE upon EC. That means BF upon FE is equal to BE upon EC, and you are done. So let us look at a trapezium once again, and using basic proportionality theorem try and derive a very interesting result about it. And the result is, if you have a trapezium ABCD where AB is parallel to CD, because in a trapezium one pair of opposite sides is parallel to each other. So in this trapezium AB and CD are parallel to each other, and if I draw the diagonals AC and DB and they intersect at point O, I can say AO upon BO, AO upon BO is the same as CO upon DO. So a very interesting property about the trapezium. Once again, somebody can simply share it as a result, but our keen interest is in finding out how this came out to be true. And by now, at least in this session, I know I'm going to use basic proportionality theorem. That means I'm interested in creating triangles and parallel lines, because that will open up a lot of information for me. So what I'll do is I'll draw a parallel line to CD or AB which passes through O. And now step by step I'll focus at triangles. So let me focus at triangle ADC. That means this triangle, for a minute if you want, forget this part of the story. So the triangle is clearly visible to you. Call this point X for a second. So I know because this line is parallel to one of these sides, it is going to divide the other sides in the same ratio. That means AX upon XD is the same as AO upon OC. So AX upon XD is the same as AO upon OC. Put this triangle back here. Now for a second, think of triangle ABC. Once again, the same line is parallel to one of the sides. That means it will divide the other sides in the same ratio. That means AO upon OC is equal to, let's say call this point Y, is equal to BY upon YC. AO upon OC is equal to BY upon YC. Actually, at this point itself, AO upon OC is equal to each other. Therefore, AX upon XD is equal to BY upon YC. AX upon XD is the same as BY upon YC. Another theorem that we have already worked out. So I've got this result, put this diagonal back here. But how do I get to this result? Because to get to this result, I want to connect the two diagonals. So far I'm only staying with this diagonal, AO and OC, some results I've got, right? So let me think of this diagonal. That means I'm now thinking of triangle DBC, triangle DBC. For a second, forget this line so that the triangle is clearly visible to you. So I'm thinking of this triangle. This line is parallel to one side of the triangle. That means this line will divide the other sides in the same ratio. That means the ratio of BO and OD is going to be the same as the ratio of BY and YC. So write that down. BY upon YC is the same as BO upon OD. BO upon OD. Now you see BY upon YC is common to both of these equations. AO upon OC is equal to BY upon YC. BY upon YC is also equal to BO upon OD. That means this is equal to this. That means AO upon OC is equal to BO upon OD. Just play with this a little and you will come to this result. Move this BO here and this OC here and rewrite as CO, and you will get that AO upon BO is the same as OC upon OD.